In this section, we're going to look at convolution properties. This is section 2.5 of the textbook. I've included table 2-1 from the textbook here, which shows the properties. What we're going to do is we're going to select two of them and do a proof, just so you can see how we can prove these properties using techniques and tools that we already have. And then we're going to give a couple of examples of how the properties are used. We are going to be proving the convolution with an impulse property. Here we have an input signal X. The impulse response is just an impulse delayed by t seconds, and we're going to prove that if this is the impulse response, then what the system is doing is just delaying the input by capital T seconds. So that's a property that will be very useful in system analysis and design. The other property that we're going to prove carefully is the area property. The area property is very useful for checking the result after you do a convolution, and also if we want to limit the energy or magnitude of the output, it relates those values to the input X and the impulse response h of t. So we're going to prove, using the definition of convolution itself and just a little bit of calculus, that the area under a function multiplied by the area under the impulse response, if I convolve those functions, the area of the result is just the product of the two areas. And we'll do an example with that as well, in addition to proving it. Let's see what happens when we convolve a signal x of t with an impulse that is delayed and occurs at t seconds. So that is going to be our output y of t. Now we also have that we can find y of t when it's convolving two signals according to the formula x of tau h of minus tau. We need to have a tau and a minus tau in convolution, and the signal that gets the minus tau then has t, the independent variable here at which we're evaluating the function. Now in this expression right here, this is equal to our h of t. So now we need to figure out what is h of tau. It's going to be delta at tau minus capital T. Then we perform, according to convolution, we have to mirror that. So we want to know h at negative tau. So we evaluate this at negative tau. And finally, we need to know h at t minus tau. So we have the delta at t minus tau minus capital T. So let's graph that out. Let's just do an example here, t equals 3. Well, then our delta of t minus 3 is going to look like that. Then we mirror it, so that's on the t-axis, and then we mirror it and relabel the axis tau. So it's going to be at negative. So this is delta at negative tau minus 3. And that is our h of minus tau. So now we can see when we substitute in here, tau is negative 3. Then we have negative of negative 3. So that's 3. 3 minus 3 is 0. So when tau is negative 3, we do indeed get the impulse here. And now our final step is to delay this by variable small t. So our final function, h of t minus tau, which is delta of t minus tau minus capital T, is going to look like this. There's going to be an impulse, but it's going to be t seconds to the right of -3. So that is what these steps are doing in convolution. So here I've drawn it as if small t was 1.5, and if small t is a positive number, then that delta will be occurring after time -3. So let's go ahead back to our original formula and substitute this in. So h of small t minus tau, we've just shown that that is delta of small t minus tau minus capital T. And the delta is going to be on at the time when the expression t minus tau minus t equals 0. And we want to figure out when that is in terms of tau, because that's the variable we're integrating over. So we solve for tau, and we get small t minus capital T. So now what we're going to do is we apply the sampling property of the delta function. And we see inside this integration, we're multiplying a delta function by an arbitrary function. And the value of the arbitrary function doesn't matter anywhere except at the single point where the delta function is on, and we've just shown that that's when tau equals lowercase t minus capital T. So from the sampling property, we end up sampling the x of tau at that value of tau. And there we have a proof of the convolution with an impulse property. And we see that that gives a delay. So this is very useful in system modeling and system analysis. When you want to delay an input and you want it to a copy of it to occur at the output later in time, then the impulse response that you give is an impulse at the time that is equal to the amount of delay you want. If I let capital T be equal to 0, then the output would just be the input. So you could prove that as well. If I convolve with a delta that occurs at 0, that's no delay, and I would get the signal immediately. If I have deltas that occur at negative values of capital T, so they occur for negative values of time or negative values of delay, then I am going to actually be looking into the future. So I would have a time advance would be my result. So there's a proof of the delay property. We're going to prove one more property, and then we'll do some examples using these properties. Let's proof of the area property. So we have a convolution. And now what we want to do is we want to figure out an expression for the area of the function y. So what we're going to do is we're going to take y of t itself, and we're going to integrate it with respect to time over all time. And we're going to then simplify that and see how the area y relates to the area of the input x and the impulse response h. So here we have our integral with respect to t, and it's the integral of the function y. Y is defined here to be the convolution, so I have an inner integral x of tau h of t minus tau d tau. Now I could group this like this, but the order of integration doesn't matter if I'm careful to make sure that I'm including the terms with the integrands where the variable applies. So what I'm going to do here is I'm going to recognize that this term right here, x of tau, only varies with the integration over the tau variable. The h varies with both of them, so I can't quite factor that one out yet. But I can treat the x of tau separately. So here's what we do. We have the outer integral and the inner integral. And I'm going to pull x of tau out of the inner integral, and I am going to switch the order of integration. So I'm going to do d tau last, which means I'll do integration with respect to t first, and I will have the h right there. So I'm doing the integration in this order. And now what we see here, if we look at the integral in this form, is we see from the point of view of this outer integral with respect to tau, I have this integral here times a function of tau. But it turns out this integral here, even though it looks like it has a tau in it, it turns out that that is going to be a known value no matter what the value of tau is. So we do this simplification. The value in parenthesis is equal to the area of the h function. No matter what the parameter tau is equal to, if I delay that function or I advance it, I'm doing that integral over all time, so I am going to just be extracting the area of h regardless of tau. So I have left this. Now I have a constant area, and I have left the integral with respect to x, of the function x with respect to tau, right there. And that integral is the area of x itself. So this is the area property, and we're going to do an example of how the area property can help you check to make sure a result makes sense. Let's do that example right now. So let's use this function as our impulse response. Let's have it go up to 4 seconds. And what we're going to do is we're going to, in the impulse response, have an impulse at time 1. And then we are going to have the impulse response be 1 volt from 2 to 4 seconds. Let's also give an input x. The input x will go up to 3 volts at 0 seconds, and then back down to 0 volts after 1 second. And the h is going to be 0 everywhere where I have not given you a different value for it. Okay, now we want to convolve these two items using properties, using graphical convolution, and we want to see how the properties of convolution help us check our work. So first thing, we need to choose which form of the convolution integral to use. Now, we can either use the form where x gets flipped or where h gets flipped. When you have a choice in convolution because it's commutative, so I'm going to choose, you want to choose to flip the simpler looking function because you have to flip one of them, which makes some things a bit more complicated, but we might as well choose the simpler one. So we'll flip x of t. So we're going to flip that, and we'll end up with x of negative tau, and it's going to look like 3 volts going from negative 1 second to 0 seconds. And that's our x of negative tau. Now that's the function now that's going to get shifted to the right by small t, and we can think of sliding this x of minus tau across h of tau. So h of tau, h is not getting moved, so I can label this graph if I want. I can just give it an alternate label. I can say this is h of tau, and this is the tau axis. If I'm looking at h of t, it's the t-axis. But h is not changing in its shape, h is not shifting. X is the one that we flip, and the one you flip is also the one you have to move. Now we could go through evaluating the convolution integral, but we'll do this with graphical convolution. Before we jump into that, let's use two properties. We just derived the area property. So we should be able to figure out what is the area of the convolution result even before calculating it. It's going to be the area of H times the area of X. And the area of H is going to be 3 because the impulse has area 1, and then I have a 1 volt pulse for 2 seconds. So the area under that H curve is equal to 3. The area under the X curve is also equal to 3 because it's 3 volts for 1 second. So if we do everything right, when we calculate our y of t, it should have area 9. Another property is going to be the width property, and this one is given in the book, but the idea is if you have h of t and it has support, it's defined on the domain from A to B, and it's 0 outside of that domain. So if t is less than A or t is greater than B, it's 0. But if t is between A and B, h has a potentially non-zero value. And x similarly has known limits. We'll call them C and D. Then the width property tells us, in the end, it's going to tell us how wide h is. But let's look at this in a little more detail. What you end up with is y of t is going to start at the sum of the starting points, and it's going to end at the sum of the ending points. So this is comes from the width property. And specifically, the width property focuses on what is the length along the time axis that you might have non-zero values. Well, that's going to be the ending time minus the starting time. So that is a statement of the width as well, but we're often more interested in the specifics of looking at, well, what is the starting point? What is the ending point? This follows from the limits of integration and from graphical convolution that the functions are 0 outside that range. We can then prove that the result will be 0 outside the sum of the ranges because of the way the functions overlap in graphical convolution. So for h here, we have a range of non-zero values from 1 to 4. For x, we have from 0 to 1. So we add those together, and we expect y to have support on the sum of those. So we add the 1 to the 0, the left side of each function, and we get 1. And we add 4 to 1, the right side, and we expect our graphical convolution to result to be non-zero only in the range 1 to 5. So if we do everything right, that's what we should get. Let's go ahead and do this by graphical convolution then and see what we get. So we will draw our time axis up to at least 5 seconds because that's what we expect we need from the width property. And let's have the height here go up to 3. So now what we're going to do, convolution tells us, and let's actually go ahead and write out the convolution formula here. We're writing it in the form where x is flipped. So x gets the minus tau because it's flipped about tau, the axis of integration, and t goes there. And then y is the one, h is the one that is not flipped. So tau is in the forward direction. So here we have our h of tau, which is this original graph up here, and we have our x of t minus tau. Here's x of minus tau right here, and then this t, which is the independent variable which matches right here where we're evaluating it, that t will be going to the right. So this graph right here corresponds to t is 0, but then as t gets higher, we will be moving this green graph to the right according to t. So let's go ahead and figure out what's happening. When t is 0, we just have this green graph and this graph here, and we multiply them, but they don't overlap anywhere. The x is back here. It's not overlapping the h yet. So it's going to start at a value of 0. And then I can think of dragging this x function to the right by t, and in the beginning it's back here from negative 1 to 0. So only when t gets up to 1 will it touch that impulse. So we can show that the output is 0 until time equals 1. And then all of a sudden I hit the impulse. And the impulse, we could use the convolution with impulse property here, which says the impulse happens at 1, so it just delays the input by 1 second. So there's the original input delayed by 1 second. That's the result. But what's happening in terms of the convolution integral is when I am moving that impulse, that mirrored impulse, right here, and I have moved it between 1 second, where it's going to be in the range here, 0 to 1, all the way up to 2 seconds, where it's in the range 1 to 2, and anywhere in between, the x function is overlapping the impulse. So what the impulse does is it samples x. So it starts by sampling this value here when t is 1, and it samples this value when t is 1.1, 1.2, 1.5, and eventually as I get to t equals 2, I'm right at this edge here, and it drops back down. Now, as t reaches 2, I now have x starting to touch this rectangle here. Oh, I did the height wrong, because the height is 3, because the height of x is 3. Let's fix that. Okay, there we go. So now we have the rectangle of x is moving over to the right, and it's starting to overlap this rectangle. So by the time we get to 3, the rectangle at x overlaps this far because it has moved 3 over from the beginning. So at that point, the rectangles completely overlap. When it's less than that, we are scaling up. That blue rectangle is just starting to move over the green rectangle. So what we have is that ramp up takes 1 second, and we ramp up to 3, because when the rectangle fully overlaps, that area of the x rectangle has height 3 and h has height 1, and they're overlapping for 1 second because that's the width of x. Now for the next 1 second, the x rectangle is moving across the h rectangle. So here it is at 3.5 seconds, 3.7 seconds, and we have a constant value for a whole 1 second while h is moving across. So it's like this, and then after that h starts to uncover. The right end, x starts to uncover. The right end of the shifted x is at 4.2 seconds, for example. It's 0.2 seconds out, so now my overlap is going down. So here we're doing a graphical approach to convolution. We could get the same result by formally evaluating the integrals, but we can see this will be the result. So by the time we get up to t is equal to 5, by the time we're there, we have taken this function x, which starts at 0, and we have moved it over 5 seconds. So it goes from -1 to 0, and that moves over 5 seconds. So it's going to go from 4 to 5 seconds. which is right here in this range. So that no longer overlaps the h function. So that's why it goes back to 0. Now let's check the two properties and see if they match up. The width property said we should get a result that was on from 1 second to 5 seconds, and sure enough it is. The area property said that we should have a result with area 9. Well, let's check this out. This rectangle part from 1 to 2 has height 3, that has area 3. And if I divide this up here, there's another rectangle with area 3. And I have triangles with base 1, height 3. So area 1.5, area 1.5, add all those areas up. And I have 9, as expected. 3 plus 3 plus 1.5 plus 1.5. So that matches, the support matches, and I know that my result is probably correct because those two properties are satisfied. If one of the properties did not seem to be satisfied, that would tell you that you definitely made an error. Okay, let's move on to one final example, one that's a little different, that is going to use the distributive and commutative properties, and actually distributive, commutative, and associative properties of convolution. Let's look at a system that is a little more involved as far as combining the effects of multiple impulse responses. Here we have an input x, and let's take it through two different paths. One path, and these are all impulse responses. Here is an impulse response, delta t. Using the delay property, or the convolution with an impulse property, we know that the output here is still going to be x of t. Let's put a different delta up in this path, and we'll have this one occur at t0. Using the delay property, we know we're going to get x at t minus t0 right here. Then what we're going to do is we are going to run that delayed x through another system in series. We'll call it h1 of t will be its impulse response. And then we are going to subtract actually the signals. We're going to add the original x, but we're going to subtract this top path. This structure I'm showing you here is commonly used in an echo cancellation circuit. So what we're doing is we're taking some signal x, which maybe has an echo in it. Maybe the recording was done in a room with a hard wall, and 100 milliseconds after someone speaks, there's an echo of their voice coming off the wall. And we're trying to remove that at the output here. So we like most of what's in the original signal x of t, but we're trying to subtract out just the echo. So our estimate of the echo in the system can be based in a lot of echo cancellation systems on a delayed version of the signal. Part of some adaptive signal processing applications, part of the algorithm would be figuring out what this delay is, but there's some really powerful and accurate techniques to estimate that for a lot of simple delay and reflection scenarios that you can just look at the data and have a very good estimate of what the echo delay is. But anyway, for our system here, we assume that's known. And then because this echo traveled a different path, there was a real-world system that transformed it. Maybe certain frequencies were damped. Maybe there were other things that physically happened to the signal, and we need to have an estimate of that. So that's what this filter, this impulse response represents. Is it says from that delayed echo signal, before we hear it, what impulse response does it go through? And we assume we know or can estimate well that impulse response. And now we have an estimate of, from our signal, what is the echo component, and we subtract it off. This is the basic block diagram that is used in a lot of echo cancellation, and with some modifications, even noise removal systems are based on this principle. Let's say we further want to take that signal with the echo hopefully removed, and let's say there are two features. Maybe there are certain frequencies or certain sounds that we want to enhance, and there's two separate features. And we have designed a system impulse response to enhance each of the features. Let's call this feature E and feature F. And there is an impulse response of the system that enhances each of the features. And we run the signal through each of these systems, and now we have the feature E is enhanced here, and the feature F is enhanced here, and if we add them together, now we have a version of the signal where both of those features have been enhanced. So this is a block diagram that you might have for a moderately complex signal processing system. But using properties of convolution, we can look at some things that are going on with the impulse response. In the top path, one of the properties of convolution in the top path in the left block is that convolution is associative. So what this means, let's call this signal on this branch right here y1 of t. It means that y1 of t, just using what we have so far, and then we're going to use associativity. It's the impulse response h1 of t convolve with the input to the h1 block, which is the x of t minus t0, as we can see from the diagram. But more formally, going back to the basics, that x of t minus t0, the way we got that was we took the signal x of t and we convolved it with a delta at t minus t0. Now, it turns out, and I have not proved this, but it is a true statement, that convolution is associative. So here we have an expression with some parenthesis for order of operations where we're convolving three signals in a certain order. But since convolution is associative, it does not matter what order I do those operations in. So I am allowed to write this as a convolution of these three signals, these two impulse responses and the input signal. And I can write the convolution like this. I don't need parentheses. The parentheses do not change the value. That's because convolution is associative. Now, since it's associative, I can rearrange the terms, and we often do this. We say, well, let's take the systems and group them all together. So there is the system H1 with impulse response H1, and the system that does the delay with impulse response delta at T1, and I'll rearrange it this way. And now we can group this together, and if I have two systems and I know both of their impulse responses, since it's associative and commutative, and I can do this grouping, that tells me that I could pre-compute the impulse response of what's in the brackets. Let's call it H2 of t. And then I could just convolve that with x of t. So what this does, if I know the impulse response, if two parts of the system in series, the associative property lets me convolve them. Then we also have the distributive property. So I have, let's call this signal coming out of the differencing block y2 of t. So we have y2 of t is equal to the top block, the bottom block minus the top block. So it's x1 of t on the bottom convolve with delta of t minus the top one, which is h2 of t convolve with x of t. and I wrote x1 there, but it's just x. Okay, so there, that is just x. Okay, and this is x of t. Now, the distributive property allows us to do this. Well, first of all, these are commutative, these convolutions, so I could rearrange the first one as delta t convolve with x of t. And since it's distributive, I am allowed to factor either on the right or the left, because it's also commutative, the x of t out. So the distributive property gets me this. And now that gives me a parallel combination of systems. Above here, using the associative property, we had a way to combine impulse responses for a series combination of systems. So what we're getting at is we have a way to combine in series and parallel the effects of systems. So even though I've specified this as 5 separate systems, we can combine them using these properties into a single impulse response. So why might this be useful? It might be more efficient to implement a circuit with a single impulse response than these 5 pieces separately. They're equivalent, so you have a choice at the very least of what method you're going to do. So I could further combine these impulse responses by using the series rule to combine with the 2 on the right, and the 2 items, the HE and the HF on the right, I would combine those with the parallel rule. So the parallel rule says you can add them, so the impulse response of this net system through this adder here would be HE plus HF. So I would add them. And we just found out that the result here was delta of t minus h2 of t, where h2 from the series combination we found out above was h2, that h2 is h1 of t convolve with delta t of t minus 1. So I have these 2 expressions, and now since those 2 items are in series, I could convolve them together, and I get the overall impulse response of the entire system. So I wanted to do this example because it's different than what's in your book. It's just a little more complicated, but this represents a common pattern used in a whole lot of signal processing systems. First, we want to repair the signal, perhaps by removing an echo, removing a noise, or maybe removing an interfering tone, so we have a pre-processing system. And then there are certain properties of the signal we might want to enhance in a certain application. We can build all the components separately. All 5 of these can be separately designed and optimized. And then when it's time to implement the system, we might use these properties to combine them all into one single impulse response, so we have a single system that has to be built and executed.